In this lesson, we're going to be defining systems of linear equations. What is a system of linear equations? It's more than one equation. We're going to just focus on two different equations, though. What does it mean to solve a system of linear equations? We're going to determine the solution. It's going to be a coordinate that's going to satisfy both equations. And before we actually get into the math behind any of this, we're going to talk about what could possibly happen if we're going to graph a couple of different things. So if we graph two lines, what can happen? And we're going to do a visual to this. So there'll be a couple situations, and that's what we're going to discuss. So one of the first things that can happen when you graph two lines is that they can intersect. So if you have a graph and you graph two different equations, one situation is, here's one line, here's a second line, and they cross. So don't forget that the idea of this line is when you plot your point and you apply your slope to get to point to point to point, each one of those points and the values in between are all representing a solution that satisfies that particular equation. So this line has an infinite amount of combinations or solutions, x's and y's, that will satisfy the equation. But this line also has an infinite amount of combinations that will work, solutions. So what we're focusing on is what do they share in common? What do they have in common? What solution or coordinates do they share? So we're looking visually as to where the lines will intersect. That will be our solution. So one situation is lines cross, and the solution to that will be that coordinate as to where they cross. All right. There's also going to be some classification, some names that will go with each of these systems depending upon what happens. One of them is, we're going to call this line, because they intersect and because they have a solution, we're going to classify this as consistent. And consistent just means it has a solution. But we're also going to narrow it down and say that it is consistent and independent. And independent represents that there's one unique solution. All right, so that's our first situation. Lines cross, we get one solution, and that coordinate represents that solution. And if you plugged it back in, it would satisfy both equations. A second situation is, what else can happen when you graph two lines? They can be parallel. Okay, so here's our visual for parallel. Now before we get into talking about what our solution is, I have a little side note about parallel. In order for things to be parallel, two lines, remember that they have to have the same slope but they have to have different y-intercepts. So you may even recognize that before you graph it, which is great. But they're going to share the same slope but have different y-intercepts, and they're not going to cross. So what does that mean for our solution? Our solution is, we don't have a solution. They don't have a point that will satisfy both equations. They don't have anything in common. They don't intersect. So our solution is no solution. To classify it, consistent represented that we had a solution. So if consistent represents that you have a solution, this, because it does not have a solution, is inconsistent. And that's it. there's one more situation that can happen when you graph two equations. We have them crossing, they're intersecting. We have the two lines being parallel, they don't cross, they do not have a solution. And the third situation is the lines are the same line. So when you graph it, it's going to look just like one equation, one line. But you begin with two equations, you get it ready to graph, and you end up having the same line. So, got a little side note, in order for it to be the same line, you're going to have the same slope and the same y-intercept. Alright, so that's kind of just the situation that's occurring. So, what kind of a solution does that have? It has infinite solutions. Because if you take a coordinate on this line and you plug it into one equation, it's going to work for the original equation, and it's also going to work for the other equation. That point's going to satisfy both equations. That's going to satisfy both equations. That's going to satisfy every single coordinate that you plug into those two equations is going to satisfy it. However, an infinite solutions is not enough, because not any coordinate's going to work. If you take that coordinate, it's not actually going to satisfy both equations. It's not going to satisfy either equation. So you have to go a little bit further in describing your infinite solution. It is infinite solutions, but it's infinite solutions of a certain combination. So it has to be the infinite solution that lies on that line. So infinite solution is okay, but you're going to have to add infinite solutions of one of the equations. And you only need to grab one because essentially they're the same. But as long as it works for that equation, then it's going to work for the other equation as well. So infinite solutions of that particular equation. And again, it doesn't matter which one, because they'll simplify down to the exact same equation. So that is our solution. And then we'll classify it. All right, so if we look back at the other one, when we were going to classify, consistent meant we had a solution. Inconsistent meant we didn't have a solution. So we do have consistent because we have a solution, but we don't have just one. So rather than it being independent, we're going to change the name on that one. So we have consistent because we have a solution. But we don't just have one this time. So if independent was one solution, then we're going to classify this as dependent. And that's because we have infinite solutions. So they're classified as dependent because one equation is usually just kind of a multiple of the other one. So one equation is going to be a perfect multiple of the other, so one depends on the other.